to be dealing with, and I have notes for you.
Yes. Last night was at 4.
What? You're at 4?
It was yesterday at 4.
Oh, yesterday was the 4th. I believe that's correct, yes. Okay, so a couple of these are going to be new ideas for you. Let's start with this one. This is a brand new idea for you. This is really an easy idea. There's 3 theorems in calculus we have to memorize. This is the first one, the intermediate value theorem, otherwise known, put a label up here, IVT. That's how we will refer to it, as IVT, the intermediate value theorem. The definition, if f of x is a continuous function on a, b, then for every d between f of a and b, there's a c between that, blah, blah. It's really confusing to read. It's really an easy theorem. What it says is this. If I have a continuous function that's bounded and a start point and an end point. So far, so good? Okay. Has a start point and an end point. I can use this to prove there is some y value between these two guys. So I can prove that that y value exists right there. An example of how this would be asked is down here at the bottom of the example. It says, given f of x equals 2x minus 3 on the bounded interval 1 to 4, is there any value c, an x-coordinate of c? Is there any place on that graph between 1 and 4 that has a y-coordinate of 3? That's what's asking, okay? So here's how you go about proving it. If we take this as an example right here, the first step is you always verify and state the function is continuous. I think it'll always be continuous anytime it's used in any detail. You have to write it down. F of x is continuous. If it's a polynomial, it's continuous. If it's a rational, if it has an x on the bottom, then it might not be. Okay? So that's the first step. Always verify and state the function is continuous. Step 2, always evaluate the function at the endpoints. Find f of a and f of b. So down here, I've got 1 and 4 as my endpoints. F of 1, well, 2 times 1 is 2, minus 3 is negative 1. 2 times 4 is 8, minus 3 is 5. So I've evaluated my endpoints right here. And so I know I'm between negative 1 and 5. Those are my y-coordinates, right? The question is there any spot on the graph where the y value would be 3? Well, if this is the min, y equal to 1, and that's the max, y equal to 5, does it make sense to you that somewhere between negative 1 and 5 there might be a 3? The way you write that is, write your y-coordinates down.
Can you move it up here?
Oh, I'm sorry, write your y-coordinates down, okay? Negative 1 is equal to 3, less than or equal to 5, and then write how you got those y-coordinates. F of 1 gave you that negative 1. 3 was what they gave you. F of 4 gave you that 5 right there. This is your proof that IVT works. And so since this is true, right there, IVT guarantees there is an f of x, f of c equal to 3. It's a really simple proof, okay? It's just evaluate the endpoints. If those numbers surround the points you want, then IVT guarantees it. Is that okay? We'll do several of those if it makes sense to you. If it doesn't make sense yet. Second thing we'll do today is practical trig limits. We've been doing a lot of polynomial limits. Let's do a couple trig limit problems. So on the trig limits, a couple conversions you need to know about. First off, if you're seeing tangent, you probably need to rewrite that as sine over cosine. And the reason you need to rewrite that as sine over cosine is because we have these special trig limits right here. Sine of ax over ax, ignore the h right now, sine of x over x equals to 1. That is a special trig limit. We're going to use that a bunch. And the inverse of that, x over sine of x, is also equal to 1. The a here is to help you remember that it's sine of 2x over 2, sine of 2x over 2x would also be 1. Sine of 5x over 5x would also be 1. Sine of 12x over 12x would also be 1. Okay? Whatever that number is, if it's the same in both spots, it's 1. And then we have the cosine limit right here. It says cosine, so 1 minus the cosine of x over x is also is 0 actually, not 1, it's 0. And I'm thinking on it, it's also an ax one. I'll have to go back and make sure on that one, but I think it should also be ax right there. And then we have our trig identities, sine squared plus cosine squared equals 1. Well, you can use that to substitute pieces in. So the way you're going to use this, same process as all the limit stuff we've done up until now. Step 1, you plug the limit value in. If you have a problem, step 2, if you have a problem, then use one of these properties above here to rewrite the equation. Step 3, replug the limit back in. So let's do example 1 right here. The limit as x approaches 0, I plug that in, I get 0 on the bottom, I have a problem. I have to use one of the properties above me here. Do I see sine of 2x over 1x anywhere? I do not. I do, however, see sine of ax over ax, right? Sine of 2x over 2x would work. So I can multiply the top and the bottom by 2. Giving me the limit as x approaches 0 of 2 sine of 2x over 2x. Well, look at this. Guess what? That's going to equal to 1. So that's going to be 2 times 1, which is 2. And I am done. Does that make sense?
So you just multiply whatever's left.
Yeah. And if there's an x left, we plug the limit back in. Does that make sense? We'll be good with that one. Go to the second example over here. Tangent of x. I have no special tangent functions, but if I rewrite this as sine of x over cosine of x over 2x over 1, to divide by a fraction is 2. That's reciprocal. So that's really 1 over 2x, right? Well, now I have, or I'll rewrite that a little bit, I have sine of x over 2x times cosine of x.
Would that be 2 cosine x squared or no?
What do you see right there?
You can make that a, you multiply by 2.
No, I need to multiply by 2. Look, what do I have right here?
Oh, sine x over x.
Sine x over x, which is 1. So that's 1 over 2 times the cosine of x. Now my last step is always do what? Plug that value back in. So plug a 0 in. And that's 1 over 2. The cosine of 0 is 1. So 1/2. That makes sense? You okay with that? Okay. Last one, 1 minus cosine squared. 1 minus cosine squared, what is that?
Sine squared.
Sine squared, right? If I look up here at this, if I was to bring that over here, I'd have sine squared equals to 1 minus cosine squared, wouldn't I? So that's really the limit, as x approaches 0, of sine squared over x. Well, I don't have sine squared over x.
Could you take a 1 out and just leave a sine x?
So I could take a sine squared really means
Sine x times sine x.
sine x times sine x, which is, I think what you're saying the same thing. Sine of x times sine of x over x.
And you can get a 1 out of that.
That's a 1. It's on the left with sine of x. And the last step is always to do what?
Plug in
Plug it in. Sine of 0 is?
0.
Sine of 0 is 0. Exactly right. Make sense? We good? Okay. Homework is out there. Let's start with the